Hi again, everyone. Chris Tisdell here again. In this presentation, I'm going to continue my live streams of mathematics, and I'm going to show you a test called the alternating series test, or as I like to call it, the AST. You down with the AST? Yeah, you know me. Sorry about that. Now, we're going to talk through an example, and I'll show you why the test works. Okay? All right, so let me share my screen with you. All right, does the following infinite series converge or diverge? Okay, well, let's write this out in this kind of general form here. You've got this minus 1 to the n times a sequence. Now, a sub n. Now, in this case, the sequence here would be 1 over n squared plus 2. Now, the AST, or the alternating series test, due to Leibniz, basically analyzes this a sub n. Okay, and there are, I guess, three conditions to this this alternating series test. Okay, so I'm just going to go through them one by one and sort of tick them off for this, and then I'll show you later why they come into play. Okay, when I talk about the proof. Okay, so firstly, for the alternating series test to apply, the a sub n's are positive. Okay, so that's the first thing. If you look at this, this is positive. The bottom's positive because it's a squared plus a positive number. So let's write that down. So a sub n is n squared plus 1, which is always positive, especially for n large enough. Okay, that's the first part. So that was easy. The second part involves the monotonicity of this a sub n. Okay, so what we're going to do is show that a sub n is a decreasing or non-increasing function. So let me show you how we do that. Okay. All right, so what we want to do is show that a sub n plus 1 is less than or equal to a sub n. Okay, so let's write that out. Now you can do this by induction if you like, but all we're going to do is basically replace n with n plus 1 in brackets in here. Okay, and now what we want this to be less than or equal to a sub n. Now a sub n is that, so the question is this less than or equal to that for, say, n greater than or equal to 1, or n large enough? And the answer is yes, because n plus 1 squared is going to be greater than n squared, and that's in the denominator. So this thing is going to be less than or equal to that thing. Okay, so a sub n plus 1 is less than or equal to a sub n, I don't know, for all n greater than or equal to 1. Okay, so that's the second part of the 3 steps or 3 conditions for this AST. All right, now sometimes it's harder to show the inequality there or prove it, but that one was reasonably easy. All right, what's the third case, or the third condition? The third condition, again, the analysis revolves around this a sub n, is that a sub n goes to 0 as n goes to infinity. So let's test that. Okay, now as n goes to infinity, this denominator will blow up towards positive infinity. So in the limit, this will converge to 0. Okay, so we've got this satisfied. The a n's positive. There's the a n is a non-increasing or a decreasing sequence, however you want to define that. And finally, a sub n goes to 0 as n goes to infinity. These are the 3 conditions of this alternating series test. So we can make a conclusion now. Because the 3 parts or conditions are satisfied, we can conclude that the series converges. So let's make that conclusion. So by the AST, alternating series test, our series, let's call it, you guessed it, star converges. Okay, let me box that up to make sure it's nice and clear. So we've made our conclusion. And there you have it. Okay, so just a little bit of discussion before I show you why it works, or give you some outlines of why it works. Firstly, this test can only be used to show that a alternating series converges. If one or more of the three conditions don't hold or aren't satisfied, you can't say for sure that the series diverges. So the alternating series test is only good for showing that a series converges. Okay, so let's just go back and have a look at these conditions, and I'll take a new page and I'll show you where, sort of I'll give you a rough idea of where these three things come into play, because it's kind of important, and a lot of people sort of don't really understand why these things come into play. Okay, so it's a bit tricky, but let me try to break it down for you. All right, so the most important thing with series is you have something like a partial, what's called a sequence of partial sums. So instead of summing up off to infinity, you start, now I'm going to use little n minus 1 here. It doesn't matter if it's big little n or little n minus 1. The important thing is that the series has terms that go, say positive, negative, positive, negative, positive, negative, negative, or negative, positive, negative, positive. Okay, all right, and here's a general a sub n. All right, now if I was to write that the terms of those series out, or the first, say, big N terms, you don't know whether the last term in the series is a positive or a negative sign. Okay, but so let's say consider this and the following. If I write it like this with a sub 2n here, so I'm subbing up to 2n, I'll get the following. Okay, and what will happen is the last term in my sum will have a negative sign next to it. Okay, so it goes positive, negative, and I know this last one has a negative sign associated with it. All right, and let's replace, say, big N with 2 big N plus 1. So basically, I have an odd number of terms here. Okay, you can continue that up, and you get that, and this, it has a positive sign in the last term. Okay, all right, so these are just sequences of partial sums now. Okay, so where are we going with this? Well, what we're going to do is show that the limit of s sub 2n exists, and the limit of s sub 2n plus 1 exists, and that they're actually equal to the same limit. Okay, so let me sort of break that down for you a little bit. All right, so you can see in here that this and this is the same. Okay, so what does this mean? It means that this sum is just that sum plus an extra term, right? And let's say we haven't shown it yet, but let's say we can show that the limit of this exists as big N goes to infinity, and the limit of this exists as big N goes to infinity, right? Call the limit of this, say, I don't know, big L, and the limit of this, say, big M. Now, the assumption, this assumption here, guarantees that in the limit, this has got to go to 0, right? So the limit of this and the limit of that have to actually be the same, all right? So that's where the third condition in the AST comes about. It's basically just showing, it guarantees that the limits of these two sequences, this sort of odd and the even sequences, are the same if they exist, right? Okay, so that's where the third part comes in. What about the other parts? Well, you can show that the other two parts, this sort of non-increasing condition and this thing here, show that this sequence is a decreasing sequence, right? And you can show, you use the same conditions to show that this sequence is increasing, okay? Now, if we have a sequence that's decreasing and bounded below by some number, then we know the monotone convergence theorem tells us that this converges. And this one's increasing and bounded above, the same theorem applies. This has also got to converge, okay? So the last thing, you can show this, and I think the inequality is something like this. Okay, so this increasing sequence is bounded above by A1. This decreasing sequence is bounded below by this. These are just finite numbers, right? So the monotone convergence theorem applies to both S sub 2 big N and S sub 2 big N plus 1. In other words, they both got to have limits. All right. So let me just make a note of that. So let's call it MCT, monotone convergence theorem. You're down with MCT? Yep. I know, I've done that one before. Yeah, you know me. Both S sub 2n and S sub 2n plus 1 converge. Right? Suppose that has a limit, say, big L, and that has a limit big M. This thing means, with this going to 0, means that L and M must be the same. All right? So let's call this double star. Lastly, by double star, they have the same limit. So what does that mean? The sequence of partial sums associated with the original series must converge. Therefore, the series converges. Okay, I know that was a lot to take in. There's a lot of very deep ideas going on here, but sometimes what frustrates me is when I watch a video of the alternating series test and they don't actually tell you why it's true. Okay, so at least what I've tried to do in this presentation is to give you some idea or a bit of intuition into why it's true. Thanks for watching, guys. See you all later. If you have any comments, any questions, just put them in the comment section. Bye, everyone.